Hi, my name is Helena, and today I'm going to show you the HERMIA SPECT Reconstruction software. We have a bone SPECT demonstration case loaded. On this first tab, we can look at the raw projection data, so we can see if there's any motion. We can also see a sinogram and linogram display of this data as well, so we're able to check for any motion artifacts if the patient was not able to remain still for the whole scan. We can correct for those using either manual correction or automatic options. For the reconstruction, this can be pre-programmed into your clinical workflow. So normally you just click reconstruct or perform reconstructions and it does it. But for the demonstration, I'm going to show you the parameters that we're using. So we're going to use our new Bayesian Reconstruction tool. The algorithm uses the underlying CT Hounsfield units to help guide the SPECT reconstruction. So that's just one of the options that we have here, several other Bayesian options and standard OSEM reconstruction as well. We have a great white paper on this application if you'd like more details. You can see here the range of radionuclides we support, also for the variety of ways in which different manufacturers' cameras present the information in the DICOM file, so maybe summed or a lower window separately to an upper window or both windows together in the same file. Really, we've put lots of work into this application to make sure that we can support raw spec data from all the different camera manufacturers. And you can see a big range of available radionuclides here and combinations of radionuclides as well that you might scan simultaneously where it's going to correct for the down scatter between the peaks. So for us, this is the standard technetium bone scan. We're going to use attenuation correction based on the CT. This is an internal CT, which means that we did the CT simultaneously with the SPECTs on a SPECT CT scanner. But if you don't have a SPECT CT scanner, if you just have a standalone SPECT, you can bring in an external CT. So if you have connection to your PACS, you can bring that down into the HERMIA software, load that into the application, and then align it with your raw SPECT to be able to use that to provide a mu map. Also, we're going to apply resolution recovery. So here we have the standard Gaussian model of resolution recovery, pre-populated with the correct diameter and length of the collimator, holds, and other options here too. So we know these numbers for all of the manufacturers' cameras and collimators, so we can provide that data to you for your scanner to set up. So this model, this Gaussian model, works really well for isotopes that are well collimated, such as technetium, but for stuff that's more penetrating, that just goes straight through the collimator and has many other collimator interactions, such as scatter or absorption in the collimator septa, and then emission of a K-edge X-ray from the collimator. We have a much more advanced Monte Carlo model, which does this full interaction modeling. This is available for holmium and different scanners, I123, I131, yttrium-90 as well. We model with a Brehm-Strahlung algorithm. And this, if you don't see your collimator and scanner selection here, we can also make this for you. So if you let us know what you need, we can redo the Monte Carlo simulation for your particular point spread function that you're going to be seeing, and then put that into the application for you to use. This application performs Monte Carlo scatter correction. We do not support any energy window-based scatter subtraction. We think that this Monte Carlo method is better in all circumstances, and we have a lot of publications in peer-reviewed journals that support this algorithm and all the varieties inside it. So here we are saying that we're going to simulate this many photons going through the CT. So basically the algorithm checks the center of the energy window that we are imaging and then simulates those photons of that energy and this energy resolution going through this CT, and does that as part of the iterative loop and subtracts the scatter out of the reconstruction. So after doing those lots of accuracy compensations with attenuation correction, scatter correction, and resolution recovery, we now have accurate enough data to be able to convert to becquerels per mil to get a sensitivity factor. So you can measure this factor for your scanner using just a uniform phantom scan, and then type it in there, what you find. So this is counts per second per megabec. Save it in your protocol, then you can apply this to your patient scans. Okay, so that's the protocol. Let's click Perform Reconstructions. So the first thing the software does is a pre-reconstruction. So what it's going to show us now is a quick preview of how the recon is going to look overlaid on the CT. This is important. Well, it's important if you've got an external CT, so at that point you can make the alignment, but it's also important in case perhaps your patient may have moved between the CT field of view and the SPECT field of view, and in that case you can use these motion correction tools to automatically line it up or manually line it up if you need to. For us, this looks good, so I'm going to click continue. So now the reconstruction algorithm is running the iterative loop. This application also supports multi-bed SPECT. So if you acquire 2 or 3 bed positions, it's able to stitch those together, and then you can use that for your reconstruction. Okay, so the reconstruction is now done. And the last step is to enter the activity and weight of the patient, just as you would for a PET scan. So we're going to be getting the output of this in becquerels per mil or SUV. So in that case, we need to know this activity to get those calculations. So let's put in an activity of 800 megabecs for this bone SPECT scan. This weight has been brought directly from the DICOM header, so where that's available, that will be brought in. Otherwise, you can just type it in for yourself. So you can click Save to save that reconstruction back to the patient database, or we can click on the Viewer button to launch it straight into our viewing software to take a look. So we can see a very nice reconstruction in front of us. So we can see the MIP, the SPECT MIP on this side, overlaid with the CT fusion here. And these, we can see we've got SUV as our unit as well. So in this way, just a really simple, easy way of getting SUVs on your SPECT. So we can see we've got really great quality SPECT reconstruction, really excellent resolution on these scans. In fact, the resolution is so good that maybe you don't have to inject quite so much activity for your scans, or perhaps you can reduce the acquisition time to do a half-time acquisition and still get sufficient quality for reporting. Thank you for watching this video and for your interest in HERMIA software.